everybody. My name is Hagay. I'm an engineering manager with Facebook AI. And today in this talk, I'm going to talk to you about recommendation systems, how to build it, leveraging deep learning and PyTorch as the deep learning framework. Okay, so let's start with the first topic in our agenda, the business problem we're solving. So at a high level, recommendation systems try to answer the question, what item will the user be interested in? And that item can really vary in terms of what it actually is based on the domain we're serving. So it can be about what product to buy in an e-commerce site or application, what restaurant to go to for dinner, what song to listen to next, what movie to watch, or what post I want to read on my favorite social media site or app. And the list actually goes on. And it's a recommendation is a pretty common problem, especially when the catalog of available items grows and is in the millions or even billions, and also as the number of users grows. All right, let's shift gears and look into how such systems are usually architected. So there's two main systems at play here. The first one is the offline system. We can also refer to it as the machine learning pipeline. The objective of this system is to, first of all, produce an up-to-date and accurate model. Secondly, evaluate that model. And lastly, take that model that was trained and evaluated and is deemed to be good enough, and then publish it to production so it can actually serve actual customers. The metrics that are usually factored in for such a system is the first one is the offline model accuracy. And there are different metrics. It really depends on the types of model, the types of problems, but MAE is one, root mean square error is another, precision at K or recall at K, and there's a bunch of other common metrics you find. And the second metric is more on the system. What's the reliability of the system? And things like the failure rate, the mean time between failures, etc. That's really important, especially when publishing the updated model is super critical. You want to minimize these reliability issues and maximize these metrics. The other system is the online system, and that's a serving system. The objective of the system is to improve the business metrics through recommendations, serving tens of items out of a much larger catalog, sometimes in the hundreds of thousands or millions. And another important factor here is that this system usually needs to have really low latency because many times the system will actually serve users as they are using the service. So low latency is critical. The other objective of the system is also to log all the user and system activity so that there is data to feed the offline pipeline we discussed earlier. This system is where a lot of the data that is used for training is coming from. Things like, what model was used, what was the items that were served to the user, what was the user context details, what was the items context detail, all of that need to be stored. Of course, most importantly, what items did the user actually interact with, right? And what kind of interaction was it? If it was a movie that was surfaced to the user, did the user actually click to watch the movie? Did the user rate this movie high, etc.? The metrics for such a system, first and foremost, the business metrics. And again, the business metrics depend on the application itself, but things like engagement time with the service, retention rate, revenue, click-through rates, etc. System performance is another key factor. What was the latency of serving content to the user? What was the memory and CPU usage of the system, etc. Now, if you look at the diagram, the schema we have here, it shows at the high level how these systems are typically built. It starts with a request coming in from the user itself, usually using a mobile device, for example, or a laptop or whatnot. That request, which contains all the query context, goes into the recommendation system. And then the recommendation system itself has these three common major phases. The first one is retrieval, and that phase is about just using the initial query or context coming in with the request and retrieving a large set of items out of a huge catalog that are very likely to be relevant for this user. So the focus in retrieval is not necessarily about finding and ranking the best items, but rather taking potentially hundreds of thousands or even millions of relevant items. And based on the input coming in, finding, say, a couple of hundreds or a couple of dozens of potentially good items, not necessarily with a specific ranking among them. So low latency, low accuracy. That output from the retrieval stage goes into the ranking stage, which is usually higher accuracy. Usually it's also a bit more complex model that requires more memory, more compute. And this ranking stage is really good at taking a couple of dozens, for example, of items, and then providing high accuracy ranking across these dozens of items, really to figure out what's the best items to show to the user, right? So that's a bit more complicated task. There's a bit more latency budget for this stage. And the output of that stage is what we expect the user to want to engage with. Now, the last stage here is actually a stage where there is a bunch of business rules that are applied on the output from the ranking stage. These business rules are typically, hand programmed. They're more manual, and they include things like filtering out maybe content that the user had, seen before, or the user may have expressed an explicit request not to see this kind of content. It may include things like there are some business rules about how we want to provide more diversity with the items we show to the user. So maybe we want to not show the same type of content one after the other, but maybe spread it and sprinkle it a bit with different types of content to make the result shown to the user a bit more interesting. The output from this stage goes into the device itself to render this content to the user. And last but not least, whatever the user sees and interact with is logged to be used later with the offline system for training. Okay. So moving on. The topic we'll focus on in the rest of the talk is actually the ranking stage, this high fidelity, high accuracy model. We'll talk a bit about how this can be built with neural networks and using PyTorch. So we take an example use case of movie recommendation. The goal is to recommend a handful of movies to watch, say tens of movies, out of a much larger catalog of tens of thousands to drive engagement, retention, satisfaction. So given a user in a movie, we want to predict the star rating. This user would rate the movie, had the user watch the movie. And we'll use a movie lens dataset, which is created and maintained by a group lens research group out of University of Minnesota. So let's take a look at that dataset real quick. There are multiple versions actually of movie lens. In our example, we'll use the one targeting education, ML-latest. It has 27 million ratings across 280,000 users and 58,000 movies. While 27 million is a large number of rating, it's actually this dataset is highly sparse, as are many other datasets we work with for recommendations. This notebook actually allows us to explore the dataset a little bit. You can access it by yourself, the notebook. It's linked in the deck. Don't need to spend too much time on that. Just a bunch of code here to load the data into Pandas data frame. You can see this code and try it out yourself. And then there's some exploration and visualization of the data. So you can see that the rating data frame has maps from user ID to movie ID, the rating, and the time step at which that movie was rated by the user. And you can see that there are tags for every movie of the genre. This is a small subset of the user item ratings. And interesting to see that, the most highly rated movies are Shawshank Redemption, Forrest Gump, and Pulp Fiction, close to 100,000 ratings. And then there's a lot of other movies that got only one rating, and usually it's actually pretty low rating. You can see that this is a logarithmic histogram of the rating count. So you can see that a small set of movies had a lot of rating, and then there's a long tail of movies that had very few ratings. You can see the distribution of the rating, where it looks like it's normal distribution, centered around 3.5. So we'll start with a simple baseline. So later we can compare the more complex modeling we do to this baseline. And the baseline we use here is popularity, which is a pretty simple idea. Given a movie, and a user will predict the user rating to this movie to be just the average rating for the movie across all other users who rated the movie. There's an edge case here because some movies, for example, maybe it's a new movie, it was not rated, or there are a lot of movies that have no rating. So for those movies who have no rating, we'll just default to 3, the middle value in the 1 to 5 scale. And that's how we'll handle this edge case. So there is a notebook linked here that actually implements this model. It's pretty simple implementation. We took 80% of the ratings as the training set, 20% as the test set, and we computed the root mean square error for this popularity model. It was 0.965, which is not very good, but also not very bad. And it's nice always to see how with very simple techniques, you can actually achieve some nice baseline results. So again, there's a notebook here, linked here, that you can check out the implementation of the popularity model, but we'll skip it just because we don't have enough time. The key question is, okay, can we do better than this popularity model? Of course, using more sophisticated techniques. So we'll start by exploring using something called neural collaborative filtering, NCF in short, for this task of star rating prediction. NCF was introduced in a 2017 paper. The paper is linked from the deck. The architecture of NCF, the neural architecture, is available on the slide. I actually pasted it from the paper itself. And just to quickly go through this architecture. So the inputs for this model are the user ID and the movie ID. And the input layer basically takes these 2 IDs. Then it uses an embedding layer to project these IDs, these sparse inputs, into dense vectors. And these dense vectors represent our latent representation of the user and the movie, in our case. And then these 2 dense vectors are concatenated together and then fed into an MLP, a multi-layer perceptron, in order to model the user-item interactions. And then the last layer, the output layer, is basically the output score to predict the star rating. So that's the architecture, neural network architecture. I note that NCF, the paper, actually proposes an additional, more advanced design, NeoMF. I'm not going to go into implementation of NeoMF, but I'll show you the code on how to implement NCF, and taking it one step further to implement NeoMF is actually difficult, and you can see the gain you get with this architecture. Let's take a look at how we implement NCF with PyTorch. And again, there is a notebook that is linked here that you can try out yourself. So this notebook covers 3 things. First of all, it starts with the data preparation, similarly to what we've seen in the notebook earlier. Then it does the model authoring. It builds the NCF neural network with PyTorch. And lastly, it does model training and evaluation. We won't go into all of this notebook here because of lack of time, but I do want to quickly jump through the model authoring so you can see how straightforward it is to build NCF with PyTorch. So this is the code. So we import in Torch, and from Torch we import NN, and then we use some of these capabilities. So we define a class, neural collaborative filtering net, that extends PyTorch's NN.module. And then this class basically encapsulates the NCF neural network with a configurable model architecture, and you configure it through the initializer parameters. So the parameters, the first one is, or the first 2 are the user count and the movie count, and just the number of unique users and movies in the dataset. And we use this when we create the embedding tables that we'll see in a minute. And then there are optional parameters that really allows you to kind of configure the neural network complexity as you see fit. So parameter for what's the embedding size you want to use for the embedding layers of the user and the movie. And then the number of hidden layers in the MLP, and for every layer, how many units to have. And then dropout if you want to configure one. And of course, the output range, which we default to 1 to 5 because that's a star rating tasks. So these are the initializer parameters. And you can see that we create the user embedding just using PyTorch nn.embedding with the user count and the embedding size. Similarly for the movie, we create the MLP with the helper function I created here. Let's take a look at that helper function, gen MLP. So you can see the helper function pretty simply just iterates over the number of layers of the MLP that you provided in the initializer function. And then for each one creates PyTorch nn.linear layer. On top of that adds PyTorch nn.relu for the nonlinear activation. And then if dropout is configured, adds dropout as well. And then goes to the next layer and the next layer until we've iterated on all the layers that were configured. And then lastly, it adds another linear layer that ends with has just one unit because we want a single scalar output. And then adds a sigmoid non-linear activation. And we're using sigmoid here because we want a range of 0 to 1. And then wraps everything, all of these wraps with a PyTorch nn.sequential. And then that is returned. So that's basically it. And then there's initialization of the parameters with random values. And then lastly, the forward function, which you have to implement for PyTorch nn.module, defines basically the forward path of the neural network. It takes two inputs, right? The user ID and the movie ID. These are the inputs for our network. And then very simply, first, it takes the user ID, feeds it to the embedding layer to get a set of user features. That's the dense vector we discussed earlier. It does a similar thing for the movie embedding. It then calls torch.cat to concatenate these two feature vectors for the user and the movie. It then feeds them to the NLP we just defined earlier. And the output is normalized to the 1 to 5 star rating range. That's it. There's a bunch of code later on to kind of test this, a forward pass a prediction on the model and then handle the model training and evaluation. I'm actually going to skip this here because we don't have enough time, but you can always check out the code yourself. Okay, so now with NCF, let's take a look. What is the performance of this NCF model that we've built? So the data was 27 million samples, just like the baseline model that we used, the popularity model. We're using 80% of the data for training and 20% for validation. The architecture that we're using here, 32 embedding size per feature, 4 dense layers, starting with 64 units down to 32, 16, and the last hidden layer has 8 units. We're using ReLU activation, ADAM optimizer, MSC as the loss function, and then a bunch of other pretty standard hyperparameters. What does it give us? So the results are not bad. We are able to beat our popularity model by 15%, get a root mean square error of 0.821. And you can see the learning curve here. The blue line is the train loss, and then the orange line is the test loss. And you can see that around the 3rd or 4th epoch, that's basically where we got the best results, which indicates there may be overfitting here with the model, but the results are pretty good. So not bad for the initial implementation. And the key question, of course, is can we do better? So now we'll take a look at how we're optimizing our model. So when we think about further optimizing our model, we have at a high level 3 major things we can look at. The first one is the data. Can we get more data? Can we get better data? Can we get additional features to train on? Can we clean up our data in a way, etc.? All of these are good ways actually to optimize the model. The second aspect is the model itself. Can we avoid overfitting using regularization? Can we increase the capacity of the model using more layers, more units, more sophisticated modeling techniques? Lastly, the algorithms themselves. Can we tweak the hyperparameters to squeeze more accuracy or allow the model to train better? Can we use a different optimizer? Can we use different initialization techniques? There are a bunch of things we can do on the algorithmic side. We'll start with trying to get more data. Now, our NCF model baseline, as I mentioned earlier, may be overfitting because when you look at the learning curves here, you can see that the minimal loss was achieved after just 3 epochs, which is really a small number. The train loss kept improving while the evaluation loss got worse. And it looks like our model was kind of, on the training data, it was getting better, but not on the test data, which indicates the model was learning the noise rather than the signal itself. Additional data for training is likely to help our model do better and avoid overfitting. And when we implement learning with more data, these are the results we get. We can see that increasing the number of examples by just 14% actually improved our model by 0.6% versus the NCF baseline, which is a total of 15.4% versus the popularity model. And this plot here actually shows how more data actually yielded better model accuracy. And there's a strong indication that had we had more data to train on, that would have gotten better. So in this case, it's very easy. The best data is more data. Not always, but in this case, at least, it holds true. So that's one exploration. Now, let's look into model capacity. So if we increase the model capacity, make it more complex, it enables the model to learn more complex representation of the interaction between the user, the features of the data. It allows to learn better representation of the users and the movies. And in general, allows the model just to have more capacity of learning. And ways to increase the model capacity is, for example, we just increase the embedding size. And this way we have richer representation of the user and the movie. We can increase the number of layers, and then we get more capacity to learn the interaction between the features. Or we can similarly increase the number of units in each layer. And there's a bunch of other things like that we can do. Now, the big problem there is that this may introduce overfitting, because when you have more capacity, it's also easier for the model to overfit. The other aspect is that it also increases the training time, it increases the hardware cost, it increases the inference latency. So those are also things to consider. Now let's take a look what happened when we increase the model capacity. So this plot shows a set of richer, more complex model architectures. And we can see that as the complexity increased, so did the model accuracy, although at some point we hit the point of diminishing returns. So we start with a very simple architecture, 32 units, so 3 layers, and then 4 layers, and then 4 richer layers, and then lastly 5 layers with large embeddings. And we can see that the accuracy did improve as we done that. So I guess at a high level, bigger is better, but sometimes at some point, unless you have more data, unless you're taking care to do good regularization, you will expect to hit pretty serious overfitting. Which takes us to the next point of regularization. So another way to help with overfitting is to introduce regularization. And one useful technique is dropout. Dropout was introduced by Srivastava in 2014 paper with Hinton. And the illustration here is taken from the paper, and it shows on the left a standard neural network with 2 hidden layers, fully connected. And then on the right, you can see an example of a thin net produced by applying the dropout on the network, the original network on the left. You can see that the units with cross have been dropped. So I won't dive into a detailed explanation of dropout, but I do want to show you how easy it is to implement dropout using PyTorch. You basically add a dropout layer in your init function, the model, and then you invoke dropout during the forward pass. And if you recall in the code we've seen, there was an invocation of the dropout. And then one last thing to remember, don't forget to call the model.eval before you're evaluating or before you're doing a prediction, because the key thing is that dropout is applied at training time to make your model more robust. But when you do inference or in doing evaluation, you don't want dropout to be called. You actually want all of the neurons in your network to be invoked. So let's look at the results of applying dropout regularization. So I applied this to the baseline NCF, and you can see that on the right, the training curve with no regularization, as we discussed, was not very healthy, right? Basically, it was overfitting from epoch 4 onwards. With NCF, you can see the learning curve look much, much healthier. You can see the training set is just like before, kind of going down nicely, but the test curve, the test loss also goes down nicely and actually in this specific plot, it looks like we could have continued training even more and we get better performance out of the network. So the results when we applied dropout regularization to our complex NCF model with pretty large embedding size and 5 NLP layers actually got us to 1% improvement in root mean square error compared to not using dropout. And even 1.4% versus our NCF baseline. So that's definitely really nice results and shows the power and importance of regularization. Now, lastly, when we combine all the improvements we discussed here, putting all of them together, we're increasing the number of training samples from 22 million to 26 million. We're increasing the complexity from 32 size embeddings to 128, and from 4 layers to 5 layers. And we're adding 0.25 dropout regularization for each layer. We can see that our results actually got much better. We're able to the combination of all these techniques actually is better than applying each one separately. We got to 2.1% improvement versus the baseline NCF. That's pretty significant. And when we compare to the popularity model, we're now even much better, 16.7% better. And we look at the learning curves, they look very healthy. And it could be that had we spent more time to train the model, we would have even got better accuracy for the model. Now, important to know that these improvements come at a cost. The model size grew 4x. The training time grew actually 24x from training within 10 minutes of our original model to 4 hours. And with it, of course, also goes the training cost. And if you think about the hardware that you need for this case, right? And using the hardware more time and a cloud provider also means you're going to pay much, much more. So there are more things we could have done actually, and you could do to optimize the model. I mean, we use more data, we use regularization, more capacity, but you can figure out ways to get better data. You can use additional features. The data set we've seen actually had more features like timestamps, like tags on each one of the movies. You can use a different architecture, like we discussed. NewMF is a more advanced architecture that will give you better results. And of course, we can do hyperparameter tuning and we can play around with different optimizers. There's still a lot we can do to improve this model further. So this is the end of the talk. I hope you enjoyed it. I hope you learned something new. I want to thank you for tuning in and listening. And I'd love to stay in touch with you. This is my LinkedIn profile. Feel free to hit me up, connect with me. We are hiring in Facebook for many super interesting machine learning roles in recommendation systems, in computer vision, in natural language processing, and lots of other super exciting work that is cutting edge and the scale that is pretty unique in the industry. I want to encourage you to reach out to me, talk to me, and I'm happy to help you find a fit within Facebook. And in general, just connect with you. So thank you very much.